Okay, today I'm going to discuss with you vector functions. We'll do some simple things. This introduction is pretty straightforward. We'll get more involved later on. But a vector function is exactly that. It's a vector such that its components are a function of some parameter. Okay, in this case, the parameter is t. I'm giving you an example of one right away here. You get a negative 3t, and then the ln of t plus 1. Okay, so this is an example of a vector function, and you could dream up any kind of component-wise functions you want. We can start asking questions right away. For example, what's the domain of this vector function? Well, that's the same as saying what values of t are we allowed to use where this thing's going to return a vector to me. And I'm going to need all three components of that vector in order for it to make any sense. So to do that, if you want to talk about the domain, all you need to do is look at each component one at a time. So in this case, we would see that negative 2 is less than t, or less than or equal to t, less than or equal to 2. We plugged any values of t like that into the expression. That expression would be defined. Okay? And what you do is you go through one at a time, look at each piece. Here, any value of t is going to be fine. So t can be a member of any the real numbers. Any real number will be okay. And then for the last expression, you're going to be a little bit careful. We can't take the ln, the natural log of 0, or any negative number. That means that t plus 1 has to be greater than 0, or that t has to be greater than 1. Okay, so it looks like we have three separate domains, but if I'm asking for the domain of the entire vector function, what we need is the intersection of all these domains. So if you want, you can draw that out if you'd like. Start with this one, it's the biggest. Here it is, there's the whole real number line. And then, according to this domain, we've got to stay between negative 2 and 2, like this. Any of those numbers are okay. And I'm putting solid dots at the endpoints to indicate that the endpoints are included. And then lastly, I'm saying that for this expression, t has to be greater than 1. So we'll go over to 1 here on the axis here. Put 1, it's a hollow dot, and we can go that way. All right, so the question you ask yourself is, where can we go on this number line such that all three of these components will have values? And the only place to do that would be between 1 and 2, with 2 included and 1 not. So the domain would be 1, open parenthesis, 2, hard bracket. Okay, so that's how you do it, and every other problem basically works the same way. You're just going to have intersections of different sets. You can also ask about limits of vector functions. So let's consider a new problem. Suppose I said to you, find the limit as t goes to 0 of this function, e to the t minus 1 over t, and then the next component is 1 plus t minus 1 over t, and then lastly 3 over 1 plus t. Okay, so this is not hard to do either. All you're going to do is think of this as like three separate little limit problems, and in order for this limit to exist, the limit of each component has to exist. So one at a time, we're going to pull these out and see what we get. So the first limit is the limit as t goes to 0 of e to the t minus 1 over t. You may or may not know what that is, but that turns out to be 1. Okay, it actually is related to the derivative of e to the t at 0, but you can think about that for a minute. For the second one, the limit as t goes to 0 of the square root of 1 plus t minus 1 over t. Here, if you try and just sub in 0, things don't work out for you. We'll do a little bit of algebra here, but it should be okay. Let's multiply, I guess, the top and bottom. We'll multiply by the conjugate of that numerator. So 1 plus, or the rad of 1 plus t plus 1 over the rad of 1 plus t plus 1. And if we do that, the numerator turns out to just be 1 plus t minus 1. That's what happens when you multiply conjugates. You get the square of the first piece of both conjugates, right, minus the square of the second. So that whole numerator just turns out to be t. And on the bottom, you just have all that stuff. Well, you're going to have t times the square root of 1 plus t plus 1. Then the t's cancel. You get 1 there. And now you can sub in 0 for the first time. If you plug in 0 there, we get 1 over the rad of 1 plus the rad plus 1. No, not plus the rad of 1, but plus 1. That's going to be 1/2. So now we have the limit of the second component of our vector function. And then, without doing too much work at all, in this last case, you can just sub in 0. You plug in 0 for t, you'll get 1 in the denominator. 3 divided by 1 is 3. So the limit that we're asked for in this case is the vector 1, 1/2, 3. Okay. All right. So let's start to talk about some derivatives of vector functions. And not surprisingly, the derivatives of vector functions are just you just take the derivative component-wise. So for example, if you have this vector function, which is going to be sine inverse t, comma, square root 1 minus t squared, comma 1. And the derivative is just what you get when you take the derivative of each of those components. Well, it's not so bad. We need to recall a few things we probably forgot maybe. But the derivative of sine inverse is 1 over the square root of 1 minus t squared. And then the derivative of this next function, you need to realize, oh, that's a chain rule. So you have 1 minus t squared squared. I'm sorry, to the 1/2, my bad. We take the derivative of that, we get 1/2 times 1 minus t squared to the negative 1/2. And then multiply the derivative of the inside, which would be negative 2t. Multiply the derivative of the inner function, that is. And then lastly, your derivative of 1 is 0. You should try and simplify these things a little bit if you can. This doesn't do much. Kind of looks good the way it is. This next piece, you can see that the 1/2 and the negative 2 would divide out and leave you with a negative 1. And then you have that t also, this t over here. That's a t there. So you're going to end up with negative t in the numerator over the square root of 1 minus t squared. And then, lastly, 0. Okay. You can also do the same thing where you're asked to find the antiderivative of a vector function, which you just do the antiderivative by components. Not terrible. Okay, so you remember your antiderivative function, your antiderivatives from Calc 1. And then you can also do some other fun things. Like, for example, you can find tangent lines, and they're surprisingly nice to do. So let's give an example of one of those. Suppose r of t equals the vector t cubed, and then te to the negative t, and then the cosine of 3t. And we might say, find the tangent line to the vector function r of t when t equals, let's say, 0. Okay. So for a tangent line, we would need two things. We would need to know what position this vector function is pointing to. So we could do r of 0 right away. And if we did that, we would get 0 cubed, and then we'd have 0 times e to the negative 0, and then the cosine of 3 times 0. Okay. That's just going to give us 0, 0, and then cosine of 0 is going to be 1. All right? So you could think of that, if this is a position vector, that's the point it's pointing at right now. We can then go find r prime of t, the derivative of this thing. Well, that's going to be 3t squared. And you got to be careful with that second function. The second function was t e to the negative t. To get that derivative correctly, you need to use the product rule. So it's going to be first times derivative of second, which would be negative e to the negative t, plus second e to the negative t. Derivative of first is going to be 1. That takes care of the second component. And then lastly, the derivative cosine of 3t is negative sine of 3t times t from chain rule. All right, so there you go. You have that. We can plug in 0 there. R prime of 0 is going to give us 0. And if you plug it in the second case, you're going to get 0 for this piece. That piece will come back as 0. But this will not. When you plug in 0 there, e to the negative 0 is just 1 times 1 is 1. So this next component is 1. And then lastly, when you plug in 0 in the last one, I guess you get off easy a little bit. The derivative of, I'm sorry, not the derivative, but the sine of 3 times 0, the sine of 0 is just 0. The times 3 is still 0. So there you go. There is your direction vector. So our tangent line, we'll give it a new name. We'll call it maybe m of t or something. Or you could call it t of t, I guess, is 0, 0, 1 plus a scalar t times 0, 1, 0. If you want, you can write that in parameterized form, like x equals just 0, basically, y equals t, and z equals 1. And then the last thing I'll mention is that it's often interesting to find the unit tangent vector. So suppose r of t equals some function, square root of t, comma 2 minus t, and maybe something else, maybe t cubed. Okay, we could ask for the unit tangent vector when t equals a particular number, maybe t equals 1. All right, so this is, it's not so bad. You start off, you take the derivative, and here you go. The derivative, the square root of t is going to be 1 over 2 rad t, or like it's negative 1. It's 1/2 t to the negative 1/2, which reduces. Here is going to be negative 1, and then you have 3t squared. Okay, so the actual tangent vector there would be r prime of 1, which would be 1/2, 1 negative 1, and 3. But that vector is not of unit length. So if I want it to be of unit length, I'm going to take r prime of 1 and divide it by its norm. We've learned this trick before, that if we take a vector and we divide it by its norm, it becomes a unit vector. But it's obviously still in the same direction because I'm just multiplying by a scalar of 1 over its length. Okay? So this is going to be this vector on top divided by the square root of each of the components squared and added together. So I get 1/4 plus 1 plus 9, or 10 1/4. All right, so this becomes the square root of 10/4, or the square root of 10 over 2 is our scalar. 1 multiplied by 1 over that. So our tangent vector, our unit tangent vector, which I'll denote as capital T of t, is capital T of 1, actually, because we asked specifically at 1, would be the following. It's going to be rad 10 over 4. What I'm doing is actually, that's not true. It's going to be 1/2. We'll do it in slower pieces. It's going to be 1/2 over rad 10 over 2, comma, negative 1 over rad 10 over 2, and then lastly, 3 over rad 10 over 2. Okay, there we go. We can simplify this a little bit, I guess, but that's it. That's basically the answer. Here you're going to have 1 over the square root of 10. Here you're going to have negative 2 over the square root of 10. And then lastly, you'll have 6 over the square root of 10. And it doesn't take too much work to see that that would turn out to be a unit vector. It's in the direction I want it to be because it's a multiple of the tangent vector. If we were to square all the components, this would end up being 1/10. The first one would be 1/10. Next one would be 4/10. The last one would be 36/10. And this is just proof that it's worth checking every now and then, because if you go back up here, when I added these together, this turned out to be 10 and 1/4, which is what it is, which is not equal to 10/4. That was me being a little goofy. That's actually equal to 41/4, which will be a little bit better. So now if I went down here and I had divided by, well, it's the square root of 41/4, which is the square root of 41 over 2. But I replaced all my rad 10s with rad 41s, like I'm supposed to, then you get a much better answer here. If you notice, when I go to take the square root of this, I end up getting the square root of 41 over 41, which is 1. So for those of you who saw earlier on, when I wrote that square root 10/4 here, and you knew I was wrong, good for you. Normally I would record this, but I think it's worth every now and then you seeing me make a silly mistake amidst the problem that's really not that difficult. It happens. Don't judge me. All right, so that's it. That's your basic introduction to vector functions and some simple things you can do with it. Remember, you can find domains. Domains are just simply the domain of each component. Find the intersection of all those domains. That set, which represents the intersection of all three domains, is the domain for the entire vector function. We can talk about limits, and limits are just done component-wise. It's like 3 separate limit problems in one, but the thing that you yield when you're done is a vector that represents what the limit of each component was approaching as your scalar, in this case, approach 0, or any constant you were approaching. We mentioned that you could take the derivative of a vector function, which you do just component-wise. It's not a terrible thing. The terrible thing about it is you got to remember all your different derivative rules, which we often forget. We also learned that we can evaluate that derivative, or our vector function, and get the slope of the tangent vector at a point. We can even find the equation of the tangent line to the vector function at that point, in this case in parameterized form and so forth. And then lastly, we talked about the idea of a unit tangent vector, and I will jokingly say, just be careful when you decide to add 1 plus 9 plus 1/4, and know that the answer is 41/4. Okay? And when you're done, you can easily see that by just checking to make sure that the length of the answer you got, in this case this vector here, is truly 1, because that's what you were attempting to do.